Manager at Amazon Research in Cambridge, as well as an honorary research fellow right here at the University of Bristol, where he maintains an active presence, for example, at the Interactive AI CDT. He received his PhD in 2010 from UCL on machine learning applied to multivariate signal processing, and has, for example, been employed at Microsoft Research, where he has co-authored a book entitled Model-Based Machine Learning. Today, he will be speaking to us on the topic of research and engineering of robust machine learning systems. So over to you, Tom.
Great. Okay, let's share the screen. We tried this, so we know it works. Okay, can you see my screen?
I can see that, yes.
Great. Okay. Thank you very much for the invite and for the warm welcome. I don't think I can see questions coming up. I don't know if I'm happy to be interrupted during the talk, but maybe like if you want to do so, Sam, will you interrupt me? I guess that's the best way to do it.
Yes, of course, very happy to do that. And if anybody specifically wants to save questions to the end, there will be a verbal session at the end as well. But yes, thank you. That's a good way of doing it.
Great, great. Okay. Let's begin. So basically, I want to just start with painting a picture here. Everybody knows that Amazon has a whole ton of products that have some ML component in them. Some of them are very visible, like things that happen on the Amazon website, the robots that move around the fulfillment centers, of course, Alexa. There's ML driving the supply chain, forecasting, capacity planning, things like that. And there's the Amazon Go stores, but there's also ML in many places that you don't see as well. So it's kind of a pervasive technology. This is not unique to Amazon, of course. Like this is kind of the modern world. But I think this has some pretty big implications. Okay, so just taking Alexa as an example, and I think Alexa is a really interesting example. So what is Alexa? It's this sort of cloud-based service. So we know that when you talk to Alexa, the idea is that Alexa is learning from what you're doing, what you're saying. It's adapting to your speech patterns, vocabulary, and personal preferences, things like that. So that means that this is, by very definition, an interactive system. It's not just a static deployment of some ML model anywhere. So, if we're thinking about these kind of interactive systems and machine learning or AI that's been deployed in the real world, how do we ensure that those systems are robust? How do we ensure that they're efficient? How do we, safeguard the privacy of our customers, which is, of course, extremely important? How do we ensure that customers are treated fairly by the systems? Always good to start with the definition. What is robustness? According to Wikipedia, I quite like this, is the property of being strong and healthy in constitution. So we need our ML models to be strong and healthy in constitution. But when transposed to a system, it refers to the ability of tolerating perturbation. Sorry, I'm hearing a bit of background noise. I don't know if somebody's not muted. And in the little see also section, you'll see like see also fault tolerant system and resilience. So I think those are both interesting points, and it sort of speaks to me that robustness is a bit more than maybe what people think it is just on the surface. So we can think about maybe like a couple of different failure modes, and we can categorize these perhaps broadly into unintentional failures and intentional failures. So unintentional ones where the ML system is kind of correct in a way. You didn't make a mistake when you coded up the model or during the training process, but something happens in deployment. So there might be outliers or anomalies in the data stream that's coming in. There could be some sort of form of data set shift. We may have limited memory or other compute problems, and there could be biases in the way that the data is collected. And then there's sort of like the more sort of scary world of intentional failures. So this is maybe an active adversary trying to attack the system in some way. So the picture to me looks like this, and I think perhaps I don't know, but I think a lot of people maybe see the title robust machine learning and they just think about this like one portion of, oh, I guess you can't see my mouse cursor probably. So I'm pointing to the.
I can see it.
Oh, you can see it. Okay, so this sort of adversarial defense, that's what people mostly think about when they think about robust ML. But I actually think it's a much bigger picture. So we have to have this sort of adaptivity to a potentially changing world. We have to deal with security and privacy. We have to worry about like bias mitigation in our models and our data collection. Of course, we have to worry about adversaries as well. And then we also, want to be able to open up the black box in some way. So, some form of like transparency is also going to be an important component to this. So I'm going to like touch on all of these points during the talk. It's obviously like extremely difficult to try and cover all of these research areas in one go. So I'll sort of like go a little bit more deeply in some areas and like sketch over a few others. And hopefully I'll try and like bring it back to this complete story at the end. So beginning with the adaptivity piece. A lot of our machine learning models are trained on static data sets. We have our typical thing is we have a training set, we have a validation set, we have a test set, or we do some sort of cross-validation, whatever. And most of the models, I mean, this is not exclusively true, but most of the models assume that the world is stationary. So this is, the distribution of the inputs does not depend on the time index. But we know that the real world is not like that, right? So there's this kind of mismatch between the choices of the models that are being used and then the reality of the systems. And you could argue that the sort of democratization of ML that's been going on. So SageMaker is a fantastic resource. You can basically do like one-click deployments now. You can even do auto ML, so you don't even need to choose the machine learning algorithm anymore. You pass in your data set and it will sweep over models and hyperparameter choices and give you outputs, and a very, very high performing result. But this almost makes the problem worse in a way because it doesn't solve the underlying problem. So we need to be able to cope with changes that are happening in the world. So if we think about like how data, okay, this is maybe not true if you're doing some like statistical analysis of a fixed data set for some scientific purpose. But if we think about like web data and data that's like collected from the behavior of humans, which is most of what Amazon does, we're in this situation where data is arriving continually. It's possibly not independent, identically distributed. In fact, very probably not. We may have tasks that change over time. So this could be like trends or changes in fashions in shopping. We can have new tasks that emerge, so new product categories, new marketplaces, like, if we have, we've built our language models to work in certain languages, and suddenly we have a completely new marketplace open, which even if they speak the same language, they might have different uses of words. So like, how do we easily incorporate that? So then, if we think about robustness, it's like, how are we able to adapt to the new data whilst retaining the old knowledge, the existing knowledge? And transparency is the component that basically says, like, how can we know if our system has gone wrong? So I think that's almost as important as having a robust system in the first place, is knowing when your system has gone wrong. So there's sort of like standard approaches that people tend to take is, we just like train models on individual tasks, and we just keep retrain. It's kind of a not very scalable solution. It would be much better if we could have some form of online learning or continual learning. This is, I would say, one of the most active areas of research in machine learning at the moment. And there's definitely a lot of exciting things coming out of it. So, for a while, we've been looking at Bayesian continual learning. So, I don't really expect you, I guess some of the readers of this will instantly read this and understand it, and others won't. So I'm not really going to talk you through the details of the maths here, but essentially, what we're going to say is that we're going to like use the machinery of Bayesian inference to keep our beliefs about the world around, and we're just going to do this kind of resetting rather than like retraining a model from scratch. We're going to say, okay, the next time we see a new task or we see new data, we're going to basically use our posteriors from the previous rounds of inference. And this could be applied in many different circumstances. So this same kind of simple recursive formula can be applied just for like Bayesian logistic regression, or for Bayesian neural networks, for Gaussian processes. It can be applied to cases where you're adding in new classes. So this capital T, sorry, T is the task, but the number of classes in YT could be changing over time, for example, and this can be all handled by the same framework. So it's really attractive. We have this natural recursive algorithm. There's a caveat here, so long as you use some kind of variational posterior. So in truth, the actual like real Bayesian posterior is going to be far too complicated. It's not going to be amenable to be used as a prior distribution. So typically people make pretty strong assumptions about what the posterior is going to look like in order to do this. So just an example of this, just to sort of like put some meat on it, I guess. Here is an example of how you might use this for generative models. So the idea is that our training data here is just going to be images. So we're first going to see only zeros. This is standard MNIST type images. And then at the second sort of iteration of this, we're only going to see the digit 1. And the third iteration, we're going to only see the digit 2. And our task at each time is going to be to basically generate from any of the classes that I've seen before. So this is pretty challenging, really. Like, on the first one, okay, we've seen zeros, we have to generate zeros. But by the time we get to this third task, we've seen zeros, ones, and twos, and we need to be able to generate all three different classes of image. But it's a while since we've seen the zeros. And, for digits, there's maybe only 10 classes here, and it's not such a big problem. We can probably just exhaustively train on everything. But if we had potentially like thousands of different classes here, that's a much bigger problem. And the phrase that you'll see a lot is catastrophic forgetting, which is that if you just train a neural network to update as you see more and more data, it will just forget about the past. So the idea is that we can make use of our Bayesian posterior to hold that belief about the past. There is a caveat there, which I'll come to first. So excuse me. Okay, so the caveat is that the Bayesian solution doesn't really solve the catastrophic forgetting problem on its own. You also need some kind of model in there of the dynamics of how you expect the data to be changing over time. Because otherwise, as you see more and more data, your Bayesian posterior will start like shrinking and shrinking, because each time you see more data, you get more certain about things. And then, like as you can imagine, like as you roll this out to very, very large data sets, you'll end up with basically point masses. But at least like the Bayesian framework gives you a way of reasoning about like how my data is expected to change and how I should cope with that in the same modeling framework. But yeah, there are still some problems with this, like variational posteriors that I mentioned. They can be pretty limiting. I know there's some work going on at Bristol even about trying to have richer kind of posterior classes than the sort of naive mean field variational posteriors that people tend to use. I mentioned this point about the collapsing to point masses. And there's always the elephant in the room with Bayesian approaches. They're more computationally expensive, and they're kind of harder to train and implement and deal with. So I think the point here, rather than like hammering on about this particular Bayesian method, is that this is still an open area of research, and that means that if we're going to do this, if we're going to try and do something about it now in the real world, am I going to try and select some like hugely complex Bayesian model, or am I going to try and think about how can I best mitigate the problems using an engineering-based solution? So we've been doing a bit of thinking about this and trying to think of what a holistic sort of system would look like that wraps around your standard sort of ML model training loop that you normally see, that gives you this kind of control that you need. So you can think of some basic components that you might need. You need sort of like you need to be able to join the right pieces of data that are coming in. You might need to do some sort of sketching or compressing. It would be you really like to have kind of a shared infrastructure. You don't want to be, if you're continually training or continually updating models, you don't want them running away with memory usage and storage usage, although storage tends to be cheap compared to compute. But and the idea here is that the whole system should share the same resource constraints, really. And much in the same way that an operating system manages its own cache and deals with what should be, what's like hot data, what should be kept fresh, and what can be discarded. I think the same should be true for like an ML system. You know, keep around data that you might need for retraining or validation, and make sure that the right amount of data is there and it's updated when it needs to be. And then, of course, you need like various different monitoring and quality control systems in there. So you really should be looking at the input data. Is that changing over time? So can we have some kind of data set shift detection in there, anomaly detection, and then kind of the other end of that is monitoring what comes out of the model. So can we look at, you know, if we don't have labels available at test time, can we just look at the distribution over the predicted classes? Is that changing significantly? So if my model starts predicting all of one class when previously it never did that, that's a sign that something's going wrong. And of course, you maybe have like limited access to some true, like some ground truth that maybe comes in sometime after you've made your predictions. So you want, if you have that, you want to be able to tie that back in and make sure that you're using that. And then there's sort of, you know, automating the ML life cycle. I spoke about like auto ML very briefly, but you know, this is sort of like the way things are going, that we want to try and take as many manual steps as possible out of the actual training process, so that we don't need to worry about how we set up our cross-validation and how we do our hyperparameter optimization. And then the last component here is this model policy engine, which is, I think, a really interesting component, which is basically like, how do I make decisions about what the best thing to do at any particular time is? So, you know, if I see that my model's doing something wrong, you know, what are the mechanisms, what are the levers I have to pull? You know, it might just be kick off a training job, or, you know, escalate, you know, send a ticket out to the on-call team or something like that. But there's going to be like you know, a whole bunch of different ways that you can basically like modify the way the system is operating, and you know, that in itself, you could imagine being somewhat of an intelligent system as well. I mean, there's a possibility here that you might want to try different policies, and you could start thinking about, well, okay, you know, could I cast this as a reinforcement learning problem or something like that? So this is just a pictorial representation of the same thing, but this is, you know, sort of a data flow of, we have our streaming data coming in, and then we have like our monitoring on the input side. The data gets sent to this sort of trainer, which is in charge of like training, updating models, you know, ensembling, keeping them around, whatever it is. And then we have this sort of prediction monitoring component. And of course, we want to like link this up to any business logic that's there as well. You know, one thing that is often the case is that there are business metrics which may not be sort of directly comparable to the actual ML metrics. So it can be, you know, you can have an extra sort of source of complexity here as well. Okay. So in summary, like, I think continual learning is where the field is kind of going here. But you know, in my view, it's kind of, you know, there's these nice methods, but they're not necessarily like production ready. So, you know, I think this engineering viewpoint is also required. And you know, there's a lot of work actually to you know, achieve some of the goals that I outlined in that image. And if I've got time at the end, I'll sort of touch on that a little bit. Okay, so onwards and upwards. Maybe I'll just pause quickly. Has anyone got any questions at this point?
I do actually. Hi, Tom.
Hi, Neil.
I'm just curious, how on earth can you manage all of this? I mean, it sounds great, but I'm just trying to imagine how I could kind of have a hand in each of those cookie jars, and could be kind of overwhelming, I reckon.
Yes, right. Yeah. I mean, I guess like the point is that it shouldn't be a single person managing it at the end of the day. I mean, I don't know if you saw the title of this slide was zero touch machine learning. I mean, zero touch is maybe a little ambitious. It's like saying, it should be, zero touch implies you don't touch it. This like runs by itself and, and it does everything by itself. That's a bit aspirational, but I think, low touch is maybe the way to think of it. So it's like, if you architect it in the right way, and you have the right mechanisms in place to tell you when things are going wrong, then actually like the requirement of the human always to be on call, always trying to work out where things have gone wrong, should be reduced. Does that answer your question?
Yeah, it sounds great.
Okay.
So, can I ask a quick question about this?
Yes.
So where is the kind of incremental and active learning fit in this zero touch machine learning scheme? So where this can be?
Yeah, so that to me is in this sort of like policy engine and sort of training loop. I guess like, I mean, active learning is a good point. I guess if you wanted to do that strictly, you should have some kind of arrow here, which goes from the policy engine back to your data streams, because you want to have like active data selection as well. And that's maybe not made explicit by this, but the point I made about this policy engine, like, could in theory be an RL system, or it could be an active learning system, is that's the point here. So you have your underlying ML system that's being controlled there.
Yeah, that makes sense. Yeah, thanks.
Hi, I have a quick one.
Okay.
And you mentioned transparency and explainability in the outline of the circular figure that you were defining to use robustness.
Yeah.
Does that feature in your machine learning zero touch model as well?
Yes, and I will get to it. I mean, briefly, just to say, transparency to me is sort of on this box around prediction monitoring and things like that. It could be, I think the phrase here could be expanded about a bit as well. Yeah. I will try and get to that. I realize that I've been hugely ambitious with time here, so we'll see how we do. Okay, so I'm gonna switch to security and privacy here, and actually I'm just gonna focus on privacy for the moment. Oh, why did it go backwards? Okay, so if we're dealing with data that's collected from naturally gathered organic human interactions with the system, we have to worry about protecting the privacy of the users. And you might just say, well, can't I just anonymize my data? And this is what people did for a long time. They started, there's this very standard algorithm, k-anonymity, which basically says, as long as I can't distinguish from at least k-1 individuals who also appear, then that's safe to reveal. So maybe here you sort of say, okay, well, if I start off with this data set that looks like this, I have this this person in the data set who's working in London in the IT department, has some salary. There's probably not enough digits these days for that, but there's the date of birth and nationality and gender. And you think, oh, okay, so what's if I reduce this to be the UK, and then I put the date of birth into an age range, and I remove the nationality, you know, is that good enough? Like, have we obfuscated everything we need to know about the individual? But this still poses a risk, right? If there are 10 females born in that age range in the whole of the UK's IT department, 9 of them could work out what the salary of the 10th one is. And the problem here that we're getting at is that this kind of thing is not robust to side information. I'm not going to go into these. I think these are all things you can look up, but basically there's been many cases now where data has been released in all good faith for research purposes, or for other reasons, and people have managed to reverse engineer information about the people contained in that data set. So this Massachusetts Group Insurance Commission was one of the first cases. There's the Netflix case, which was.
You've just muted yourself, Tom. Someone's muted you.
Oh, interesting. Okay. Can you hear me again?
Yes, can hear you loud and clear.
Okay, great. And I think if you don't know about these examples, you should go and look them up, because they are really quite scary. And the point in all of these cases is, like, the data was scrubbed and it was released to the public, but there was always some other data source that was available that the releases of the data didn't think about in advance. So what can we do about this? So there are a bunch of different sort of privacy enhancing technologies that could be used. I would say that probably the most popular one and the most, I guess, ready to use as a technology is differential privacy. So differential privacy, formally speaking, is a randomized mechanism. And we say that we have this like epsilon differential privacy if for 2 neighboring inputs. So that's basically like if you have, if you can think about it like this, if you have a database and a neighboring database where you just changed the data about one individual, so you've either like removed an individual or added one in, or somehow changed what's in there, that you shouldn't be able to tell the difference between those 2 databases. And it's actually, it's a probabilistic bound that you get, which is kind of interesting in itself. It's it's not deterministic. It's only defined in high probability, but it sort of protects you against these the exact kind of attacks that I was describing before. So like a really simple way of producing a differentially private mechanism. So this was obviously like in 1965. This was before the definition of differential privacy, but like later on, the DP researchers realized that actually this super simple mechanism is differentially private. So basically, if you want to release a bit of information, so just yes or no, you flip a coin, and then if it lands tails, you respond with the truth. If it lands on heads, you flip a second coin, and then you just respond according to what the coin said. And you can compute what this is. This basically tells you that e to the epsilon is 3. So this is like log 3 differential privacy, and it's just a pretty simple computation of the possibilities there. So some important properties about this: we have robustness to post-processing. So if you have a differentially private mechanism, then any function that's applied, any operation that you apply over the top of that, is still at least epsilon delta differentially private. We have this nice composition property, which is if we have several different differentially private mechanisms, then the combination of those is just the sum over the epsilons and the sum over the deltas. And probably the most important thing is this point about it protects against arbitrary side knowledge. So there's nothing you can do as an adversary by adding in side knowledge that will undo what differential privacy does. So, you know, there's always going to be a trade-off here. So basically, like the way this works, in that coin flipping example, we saw, you know, we are adding noise to the answers. In expectation over a lot of answers, you know, if we did that experiment a lot of times, we'll still get the right answer in expectation. But for smaller numbers, then you know you now have noise in your data, and basically like the epsilon that you have, like in that coin flipping example, we had a fixed epsilon. But you can imagine if it's not just a simple coin example, but something where the epsilon can actually be moved, we then have this sort of trade-off between privacy and utility. And you know, an example here is, so this is pretty popular these days, differentially private SUD. So you could basically make any neural network differentially private by just slightly modifying the algorithm. So you basically have this noise variance that you add to your gradients, and then you do this gradient clipping as well, which is just needed there to make the proofs go through. And then you have this you basically have the differential privacy guarantees for any neural network that you can train. This poses a problem though, which is that you now have extra hyperparameters. So you had all of your neural network parameters that you already had, your batch sizes and epochs and learning rates or whatever. But we now have two extra parameters from differential privacy. And you know, optimizing simultaneously for utility and privacy is going to be a challenge here. So just like in pictures, what this looks like is we have a bunch of we have this like hyperparameter space, which is, as I said, is like your neural network parameters plus your privacy parameters. And then, you know, at each point in the space, you're going to get a something like a test error or you know, some way of evaluating your model plus some epsilon value. So basically, depending on how you set all of your hyperparameters, you'll get a different privacy loss. And interestingly, like the privacy guarantees depend not only on the hyperparameters of the differential privacy, they also can depend on the neural network hyperparameters as well. So for example, like, because you're adding noise at every single gradient step, if you have more batches or, you know, or if you stop early, you're going to have a different incurred privacy loss than if you ran for longer. So if you run this a few times, you know, you have a different set of hyperparameters, you get a different error and privacy loss, and we keep going. And then eventually what you'll be able to do is sort of draw out, you know, you'll be able to describe what's called the Pareto front. So these are the Pareto optimal points, empirically speaking, which is to say that, you know, for any given privacy loss, I can't achieve a better error than this, or the vice versa. For any given error level, I can't achieve a stronger privacy guarantee. So, you know, a question might be, like, how do I find the best place along this? So you could just do this empirically. You know, if you have enough time and money, you could train many models. But you know, you might also want to sort of optimize this Pareto front. So again, I won't go into the details here, but this is a piece of work we did looking at using Bayesian optimization in order to directly optimize this Pareto front. Okay, so to sum up on this topic, you know, again, I think this is active research and is kind of borderline whether you want to call this production ready in a way. I think, you know, one of the hardest things is to convince stakeholders that a particular epsilon value is meaningful, and that the utility loss is acceptable. You know, people spend a lot of time driving for utility gains. So if you tell them that there's going to be a utility loss, you have to justify that. Okay, I'm going to pause again. Any questions on this?
One quick one. How big is the utility loss typically? Sort of, have you found that differential privacy really does impact performance?
Yeah, I mean, it's dependent on a whole bunch of things, as you can imagine. It's dependent on how much data you have. It's dependent on what you're trying to train. I would say that there is almost always a loss. There are some kind of weird, rare occasions where there's almost no privacy loss. And you'll find there's a paper which is called Privacy for Free. Privacy never comes for free, but you know, I think the point is, you know, I think that was specifically about linear regression, and it sort of tells you, like asymptotically, as you get more and more data, you recover the exact answer. You can kind of think that the noise here could have some sort of regularization effect. So, you know, if you took the regularization out of your model and then basically used BP instead, you might get away with it. But typically, like, you know, I would expect like a couple of percentage points difference or something like that. You know, it's definitely has an impact. And you know, as I said, like if you're trying to optimize for the like third decimal place of your accuracy, then 2% sounds awful. But if you're, you know, if that's good enough for the use case, then it's okay.
Thanks.
There's a question.
Okay.
Tom.
Yeah.
What would be some causal approaches to enhancing model robustness?
Causal approaches. Okay, I'm gonna come back to that question. I think it's a really interesting question, but I'll sort of think about that in the background. Okay, so I realize like there isn't a huge amount of time, but I haven't actually got a huge amount of content here either. So I just think it's important to sort of touch on some of these topics. I think, you know, fairness is so, you know, bias mitigation and fairness is a really also a really like pervasive topic at the moment. You know, we have certain risks, particularly I think when we have data which is collected in this sort of organic fashion. So, you know, we haven't gone out, we're not, you know, we're not like pollsters or something like that who are going around and specifically saying, okay, we want to collect data which covers like all of the key demographics and is exactly like stratified and all of that. You know, we most of the time don't have the luxury of that. So we need to be super careful, particularly if we're optimizing directly for ML metrics like, you know, accuracy or whatever it is, that we don't accidentally optimize only for the portion of our training data who were the most represented. And there's many kind of classical examples of where this has gone wrong. And I think this is you kind of think, well, okay, where's the differential privacy equivalent of fairness? And the problem is, like, unlike in privacy, there's no single agreed on definition. There are actually like many competing definitions, and they, you read them all, and you can go and find, I think there's a nice talk somewhere which is 27 fairness definitions or something like that. They all make sense. They all, like, you read it and you're like, oh, okay, this sort of like makes sense as a fairness definition. Like, then you read the other one, you're like, oh, okay, that also makes sense, but they don't really agree with each other. So I think, this is a really kind of interesting problem for the ML community. So, this is, I'll just like speak about one definition here just to make this concrete. If we think about, like, we can think about statistical bias. So that might be the difference between the expected value of an estimate and its true value. Is that a good enough criterion? And this is sort of comes into this, like, okay, well, my model just was trained on the data. My model doesn't have any bias in it. But this isn't good enough, really, because, like, I think, as an owner of an ML system, you kind of have to take ownership here. So another idea is calibration. So, you're probably all familiar with the definition of calibration. Philip Davids is a very nice one, which is, if a forecaster is well calibrated, if in the long run of events, you assign a probability of 30%, then it actually happened 30% of the time. So you can make a fairness definition out of this as well. Again, sorry about the heavy notation here, but it's like you could say, well, I could be alpha accurate by saying, like, the expectation between my predictions and the truth is within some alpha, or I could be alpha calibrated if for any probability or any point in the probability space, then the difference between that and my expectation is less than or equal to alpha. This has problems as well, though, because you can kind of game this. You can make a system that's perfectly calibrated, and just in the same way that you could, like, make a weather forecaster in the UK be perfectly calibrated by saying it's going to rain like 30% of the time or whatever. You can do this in this setting as well, just like by doing it within the sort of the demographic groups. So typically this is applied to sort of like large disjoint sets of your data, but it's kind of not perfect. There's this proposal of something which is stronger, which is called multicalibration, which is basically saying, like, the ideal thing would be to be calibrated everywhere. So to be calibrated for every possible subset of my data. Now, of course, that's impossible. The only way you could achieve that is by having perfect predictions forever. It's also computationally impossible because you can't, for any reasonable size data set, set of features, you're not going to be able to compute the power set, so the every possible subset of features. So they define this sort of like computational identifiable subset definition, which is sort of like, okay, well, I'll just randomly sample subsets, and if I have enough of those, then that's like going to be good enough. And in the paper, they argue that you can sort of throw in the typical sets that you would have been interested in anyway. So you can include your race and gender and things like that into those computationally identifiable subsets. But you're sort of somewhat protected against the things that you didn't code for. But again, I think there's not one particular notion here which is going to save us. At least these things can be run post hoc, and so you can do checks afterwards. And there are some pretty good systems for doing that these days. this last point is not clear at all. I think some of the fairness definitions will sort of like sit happier with, for example, with differential privacy than others. But I think this is like an interesting open area of research. What's the time? 7 minutes. Oh dear. Okay. So I'm just going to sort of like whiz through, and hopefully we still have time for a couple of questions. So, I mean, probably like as I said at the beginning, like a lot of people might have thought, oh, here's Tom's going to talk about adversarial machine learning, adversarial defense, and this is a component of it. But I think the fact that these two have been like tied together so heavily, to me, is a bit of a misnomer. But I couldn't really give this talk without speaking about it. So, what is adversarial ML? In general, it's like attempts either to fool the models or to steal information, either about the model or the data that the model was trained on. So we can think of like adversarial examples, and I'm sure you've all seen like the panda that gets misclassified as the whatever it is with a single pixel change. These kinds of things. That's your sort of very, very sort of standard thing. I think these are interesting, these sort of like Trojan attacks or backdoor attacks. So the idea here is like, if I'm using some like machine learning as a service, so I'm outsourcing it, then you could train your machine learning algorithm to do well on the data provided by the user, but still be able to do unexpected things on some particular data you provide. So you could basically encode those single pixel attacks into your model. So don't trust that would be like don't trust a random person to train your model for you. And model inversion is sort of like trying to work out, okay, what were the if I just have an API access to a model, am I able to work out what all the parameters are in there? And there's some interesting attacks there. And membership inference is going back to the privacy case, is like, can I work out if a given individual was in the data or a given data point? And under defense strategies, like the first 4 of these, I would say are all kind of directly borrowed from just security practices in software engineering. So threat modeling, that's what everybody does when they're engineering a robust software system. Attack simulation, impact evaluation, and countermeasure design. These are all like very, very standard practices. There's kind of nothing specific to ML here. I think this the bits that are specific, like this sort of noise detection component, that linked back to needing a good anomaly detector in there. I think if you're able to detect adversarial examples, there you'd also be able to detect just like strongly out distribution samples. And there's this sort of interesting phrase, information laundering. There's a defense strategy which is basically, I'm going to do something to the input data in order that this type of adversarial attack isn't going to work. And you could imagine here that a differentially private mechanism might actually be able to work as an information laundering system. I'm not sure if that formal link has ever been made yet, but and there's a bunch of resources here. I think there's some interesting libraries. The Robust.ml is this quite nice community-run hub where you can basically upload new attacks or new defenses, and there's various different places where you can try out different things. I've found like nearly everything is computer vision based, so there seems to be a bit of a gap here. I mean, there are probably others who are listening to this who maybe know more than me about this, but again, like I think this is still a growing area of research, and to me is not really like a solved problem at all. Okay, I promised to talk about transparency, and I'm kind of out of time. Can I ask the organizers what the deal is if we run over for a few minutes, or would you rather not do that at all?
I think in practice, a few minutes should be fine, Tom. So if individual members would need to wander away, that's absolutely fine. I understand we are recording the session, as most sessions are indeed recorded. So if anybody is forced to leave at 12 o'clock, this recording will be available on the website, on the JGR website, after the fact.
Okay, thanks, Sam. Yeah, so apologies to anyone who needs to leave. You can always reach me by email as well if you want to ask questions, and I'm sure Sam can provide that. Okay, so again, this is like an open area of research, and I know that again, there's people in Bristol who are interested in this. So I might be preaching to the converted a little bit here, but one of the issues that we have is like increasingly that we're using these black box or maybe gray box models. We have these like extremely complicated models. If we think of like a 12-layer BERT language model, it has 90 million parameters in it. How on earth are we? Okay, you can do something. You can look at the attention maps, and you can try and like work out different things and. But I guess a more general question is like, can I get simpler explanations about a complex model in a kind of model agnostic way? So these sort of like additive feature attribution methods try to do that. So they basically like you have your complex model F, and you're going to try and use a simpler explanation model G, which is going to approximate the complex model just in the region around a given input data point. So it's going to be like dependent on the data. And typically like what you do is like you can imagine that there's sort of like your complex model has some really like nonlinear surface around there, but you could use a linear approximation to that small region of space. And the explanation model is basically going to take a sum over the features or the effects of different features in the model. And you can just simply think of this as saying, okay, my prediction changes by a certain amount if I include a given feature or don't include a given feature. And Lime is a popular implementation of this, which sort of uses this very simple objective function where you're minimizing basically the difference between what your complex model and your explanation model says with some regularization over the explanation model. And there's various sort of different proposed methods that expand on this as well. Another popular thing which is being used quite commonly nowadays called Shapley values. So this sort of takes inspiration from game theory. And the idea is that you have a team of players with a certain payout, and you want to sort of distribute the payout according to the players in a fair way. And it's interesting, this comes back to fairness, and the Shapley values have their own definition of fairness. So everything I said about fairness and all the caveats still holds here. Like this, again, is one definition. Like efficiency, the contributions must add up to the total payout. Symmetry, if two players contribute the same, then their output should be the same. You read this and it's like, oh, okay, yeah, that's totally reasonable, all totally makes sense. But I think the authors of the paper would say, oh, this is the only fairness definition, but it's not. And then, if you're going to apply this to ML models, like your payout is now the model predictions, and the players are the individual input features. And what we're doing is we're saying like how much of the model prediction can be attributed to each input feature. And the authors claimed in the paper that this is the only additive attribution method that satisfies all of those fairness properties for their given definition of what fairness is. And I'm not going to really go into it more than that, other than say, this is kind of a popular method, and empirically seems to do quite well. Like these SHAP values, so SHAP is a particular implementation of the Shapley values. They match better with human intuition compared to other methods, but I think there's still some open questions. There's a lot of like independence assumptions that are encoded in the method, and it's not really clear what happens when you move out of distribution samples. Okay, so that was kind of like a very breathless tour of all of these different topics, and to me that that sort of like that whole thing, every one of those is in itself a research area, but that whole thing is like, that's really like, if we're going to truly achieve machine learning systems that don't go wrong, then we kind of need all of that, which does, as Neil pointed out earlier, that makes life awfully difficult. I think at Amazon, we're trying to solve some of these problems. There's a whole bunch of products in the SageMaker catalog, and really like we're trying to make life easier and make a lot of this complexity go away for users by sort of like linking up really, really good well-engineered solutions to problems. So just like two of those, so in the reInvent 2020, so just at the end of last year, SageMaker Clarify was announced, and this basically it is tackling the sort of the fairness and the transparency. So they actually have SHAP implemented in there. And they have some bias detection algorithms as well. And there's the SageMaker Model Monitor, which essentially is doing the drift detection and model quality metric detection that I spoke about before. And it links together with the Clarify service. You also get this kind of, you get drift in bias. It'll tell you if your system, which was originally not biased, has drifted and become biased over time. Okay, so just like super high level summary, machine learning requires more than just like clever algorithms, and I think we really need to think about all of these issues. I really like this book by Michael Kearns and Aaron Roth. It's quite, it's quite readable, The Ethical Algorithm. So I'd recommend a read of that if you're interested in these topics. Okay, cool. I am happy to stick around for questions a bit more, but feel free to drop if you need to.
Thank you very much, Tom, for a fantastic talk. I will applaud on behalf of everybody in the room.
Thank you.
I'm guessing there's going to be quite a few questions, quite a lot of interest. There's a lot of food for thought there. So if anybody does have a question, if they could raise their hand or type into the chat as a first port of call, that would be fantastic. But obviously, if yes, there actually already is a question in the chat. So I'll read it out for the benefit of everybody here. With monitoring machine learning predictions for distribution shifts and adapting them on the fly, is there a practical limit to how fast the system could adapt? Or are some changes likely to be too fast? For example, for goods distribution, having a national border being closed with a few hours notice, is there any hope on the horizon for systems that can be robust to rapid shifts in circumstances?
Yeah, very interesting question. Yeah, I mean, I think what that will depend on is how fast your, this bit that I call the policy engine, whatever it is that's kind of acting and making decisions on the basis of the shift detect, and how quickly that can act, and what the kind of iteration cycle is. I think if you're stuck in this like we have this gigantic model and we're going to retrain it every time we get like 24 hours worth of data in, or a week's worth of data, then you're obviously going to be stuck, because all of your, all of your scripts and everything that have to run are going to be fixed to certain time intervals. They're going to be fixed to like data collection intervals and things like that. So, if you have this case where it waits for a week until it retrains, and then, I don't know, like you say, a border gets closed or something like that, how are you going to, are you going to be able to kick off a new training job, or what's going to be the policy that allows you to update fast enough? I think as you move away from that sort of like fixed time paradigm, and you move to more adaptive systems and more like real continual learning, then you have the ability to adapt faster. It's an interesting one, isn't it? Because you also don't want to necessarily like overreact or react to every small change that's happening. So I think that's it's a really interesting question. There's kind of a flip side to it as well, which is that if the change is so slow as to be almost undetectable, then I think you're gonna have a very, very hard time actually doing anything about that.
Thanks for that, Tom. And I'm currently not seeing any hands or further questions in the chat. So I guess it means we can.
So there was there was the question about causality, which I think is really, really interesting. I would imagine okay, so if you want to do some sort of causal inference, you really have to be able to make interventions in some way. Otherwise, if you're never really going to be able to unpick the actual causal reasons of why things are happening, unless you have you actually know the causal graph perfectly. Then you might be able to do it purely from data. But generally speaking, the causal graph is unknown, has to be estimated. And then the only way you can really do that is if you make some kind of interventions. People do make interventions at the moment. They do things like A/B testing and other ways of like running auctions and things like that. But it's not very well formulated, I would say, if you do it using those methods. It's a good question. I should try and think about that more.
There is one final question in the chat, which I think we may make the last question just in the interest of time. Apologies to anybody still with questions. The AI committee at Parliament refuted with the use of machine learning models that do not provide a satisfactory explanation and advocated the use of interpretable machine learning models. Do you think we are too quick in the use of neural networks where simpler, more interpretable models can be deployed? And do you think it's fair to make such requirements become legislative?
Wow. I mean, really, really interesting topic, isn't it? I mean, I think I always have this thing of okay, are you really going to sacrifice performance for interpretability? That's one thing. Say we are designing something which is going to be a medical diagnostic. What do we care about more? Do we care about being able to interpret the model, or the fact that the model is right 99.999% of the time? And if it's right 99.999% of the time, we probably don't care too much about how it's actually working. So you kind of have to factor in what are the costs. What's for that 0.0001, maybe that's a really super, a patient unfortunately dies or something like that. That's a really, really hard sort of trade-off to make. But I think that's one consideration. The other thing is I would kind of push back on a little bit. I know I talked about using simpler models to explain more complex ones, but there are a lot of cases where simple models, although they appear interpretable, can go wrong in interpretation. For example, like if you just do a simple linear regression, and then you try and use the weights to interpret that, and you don't have, you only have like a diagonal covariance over your weights. So you've not modeled the covariance matrix. If you have correlated features in there, you're going to get incorrect interpretations out. And that is like a classical mistake that is made over and over again. So I think, just saying, oh, we need to have simple models because they're interpretable doesn't necessarily answer the question. And I don't know, do I think it's fair to make it legislative? I think they're trying to do the right thing, aren't they? But it's a really, really tricky area.
Thank you very much.
Yeah, I'll close on that. I know.
On that note,
I think commit to an answer.
I can say it's been an absolute pleasure to have you here today, Tom, and I shall give you another round of applause on behalf of the entire room.
Okay, thank you very much.
Thank you very much indeed. So the next meeting will be sometime in March. And thanks again to Tom for agreeing to speak today. This recording will, as mentioned, be available on the JGI website after the fact. Have a very good afternoon to you all. Thanks again, Tom.